Welcome back to the deep dive. Today, we are unpacking something that feels like a genuine evolutionary leap in the world of electronics.
Hmm.
Usually when we get a stack of documents about a new board, whether it's a Raspberry Pi update or a new microcontroller, the story is, well, it's pretty predictable. It's faster, smaller, or cheaper.
Right. It's the standard more specs for less money narrative. It's a comfortable story, but it's rarely a surprising one.
Exactly. But today is different. The materials we're looking at today, these technical schematics, white papers, all these architectural overviews, they describe a structural change.
A big one.
We're talking about the dual brain revolution, specifically focusing on the new Arduino UNO Q. And honestly, reading through this slide deck, it feels like they are trying to solve a problem that has been making engineers pull their hair out for, 10 years?
It is a massive pain point. It's this tension between thinking and acting.
Right.
And if you've ever tried to build a robot that does something more complex than just, driving in a straight line, you know exactly what that tension feels like.
So before we get to the shiny new hardware, let's establish the why. Why is this a revolution? Because on paper, having two chips on a board doesn't sound like reinventing the wheel.
No.
We've seen dual-core chips before.
It comes down to the fundamental difference in how computers handle tasks. You see, in the world of embedded systems, robotics, smart home devices, automated factories, you have these two opposing requirements.
Okay.
On one side, you've got high-level processing. You need to run AI algorithms, process video feeds, host a web server, talk to the cloud. That's the thinking.
Which is usually Linux, right? Like a Raspberry Pi or even a simplified desktop computer.
Correct. Linux is great for thinking. It handles complexity beautifully. But then you have the other requirement, acting.
The physical stuff.
Precisely. You need to spin a motor at exactly 2,000 RPM. You need to read a gyroscope sensor every single millisecond.
Yeah.
Not 1.1 milliseconds, not 0.9, exactly one.
And this is where the conflict starts. Because Linux isn't great at being on time, is it?
It's terrible at it. It's a general-purpose operating system. It has overhead. It has background tasks.
Right.
It might decide to pause your program for 10 milliseconds to do some garbage collection or update a system log. If you're rendering a web page, you don't notice a 10-millisecond delay.
Sure.
But if you are a robot balancing on two wheels,
You fall over.
you fall over immediately. So the developer's dilemma, which is explicitly called out in our first source slide, is this mismatched need. You need a supercomputer for the brain and a reflex system for the body.
I love the visual in the slide titled The Conflict. It's so brutally honest. It shows a Raspberry Pi on the left and a classic Arduino on the right. And in the middle, labeled The Developer's Dilemma, it's just a literal rat's nest of wires.
We have all built that monstrosity.
Yeah.
You have the Pi doing the vision processing, and then you connect it via USB to an Arduino to move the motors.
And you're trying to send commands between them.
Constantly.
And that's where the mess isn't just physical, right? It's not just about ugly cabling.
No, the physical mess is the least of your worries. It's the communication stability. You are trying to get two completely different architectures to talk through a straw, usually a serial connection or USB.
Right.
The slide mentions timing mismatches and unstable communication as major risks. If that USB cable vibrates loose for a microsecond, or if the serial buffer fills up because the Pi sent data too fast,
Your robot just freezes.
it freezes. Or worse. So you're essentially managing two different code bases, two different power supplies, and this fragile little bridge between them. You're spending more time being a plumber than an engineer.
Exactly. You spend 80% of your time debugging the connection between the brains and only 20% building your actual robot.
And that is the problem the UNO Q exists to solve.
Which brings us to the answer. The Arduino UNO Q. Now, visually, looking at the diagram here, it looks deceptively simple. It's that classic teal Arduino color, same form factor.
Yep.
But the silicon on top is telling a very different story.
This is where we see the dual brain concept made physical. Instead of, duct taping two boards together, they have integrated both distinct architectures onto a single printed circuit board.
Let's meet the team. The slide breaks it down into the thinking brain and the acting brain. Let's start with the heavy lifter. Who is doing the thinking?
The thinking brain is a component from Qualcomm the Dragonwing QRB2210. Now, for the non-chip nerds out there, this is an MPU, a microprocessor unit.
Okay, let's pause on MPU for a second. So explain it like I'm 5. How is an MPU different from the chip on a normal Arduino that people might be familiar with?
A normal Arduino uses a microcontroller, an MCU. It runs one program in a loop forever. It's very simple.
Right.
An MPU, like this Dragon Wing, is designed to run a full operating system like Linux. This chip has 4 ARM Cortex A53 cores.
Cortex A53. That sounds familiar. That's smartphone architecture, isn't it?
It is. It's the same architecture you'd find in mid-range smartphones or tablets. So it brings serious power. It has an Arduino GPU for graphics and, crucially, a Hexagon DSP, a digital signal processor, specifically designed for AI inference.
Okay.
It handles Wi-Fi 5, Bluetooth 5.1, all the heavy math. It is the philosopher of the pair.
So we have a smartphone-grade brain on the board. But you just said the philosopher is bad at balancing, so who is the athlete?
The acting brain is an STM32U585. This is a high-end microcontroller unit, an MCU. It runs an ARM Cortex M33 core.
And its job is just to listen to the philosopher.
Its job is to handle the real world. It handles the GPIO pins, the general purpose input-output. It controls the pulse width modulation, the PWM, for motors. It reads the sensor.
That's deterministic.
Exactly. Because it's a microcontroller, it is deterministic. That means if you tell it to do something every millisecond, it does it exactly every millisecond. No excuses, no delays.
So we have the philosopher and the athlete living in the same house. But I noticed a note at the bottom of the meeting the team slide that I found really interesting. It says, critical feature, independent operation.
This is huge for safety. In a traditional computer, if the operating system freezes, like when you get the blue screen of death.
Everything stops.
Right, everything stops. On the UNO Q, because the MCU, the athlete, is physically a separate chip, it keeps running even if the Linux side crashes.
Oh, wow.
Imagine you're building a drone. The Linux side is processing video to see where to land. Suddenly, the video software bugs out and crashes.
In the old setup, the drone stops sending signals to the motors and it just drops out of the sky.
Exactly. But here, the athlete is still running. It notices the brain has gone silent, but it keeps the propeller spinning, maybe enters a hover mode, and waits for the brain to reboot. That separation is vital for industrial and robotics reliability.
That is a genuine game changer. It's like having a reflex system that works even if you're knocked unconscious.
That's a perfect analogy. You don't stop breathing just because you're thinking hard about a math problem.
Okay, so we have the hardware. But I'm looking at the next slide, the high-speed highway, and I'm playing devil's advocate here. If they are separate chips, don't we still have the communication problem? We don't have wires, sure, but don't we still have to write code to make them talk?
You've hit on the hardest part of dual-chip systems.
Yeah.
Usually, yes, you'd have to invent a language. You'd write code saying, okay, if I send the number 1 over the wire, that means turn on the light. It's tedious.
Very.
But the UNO Q uses something called an RPC bridge.
RPC, remote procedure call.
Exactly. And this is the secret sauce that makes this board usable for normal humans.
How does it work?
Think of it like this. Usually, if you want to ask your neighbor for sugar, you have to write a letter, put it in an envelope, mail it, and hope they understand your handwriting.
Right. That's serial communication.
Slow and prone to errors. RPC is like telepathy. The code examples here are wild.
Yeah.
On the Python side, which is running on the main Linux processor, they define a simple math function, just add AB.
Okay.
And the C++ side, the microcontroller, can just call it. The code literally looks like bridge.call, add 1.0 or 2.0. It calls the function as if it were inside its own brain, but the computation magically happens on the Linux side.
And it works both ways.
Yes. The microcontroller can expose a function like settled color, and the Python script on the Linux side just calls settled color red. It handles all the data serialization, the timing, the memory mapping. It does it all in the background.
That removes an entire layer of engineering. You stop thinking about, how do I send this data, and you just start thinking about logic.
It collapses the complexity.
Yeah.
You're just writing software. You forget there are 2 chips. It becomes one unified system.
This leads us nicely into the workflow. Because having great hardware is one thing, but if the software experience is miserable, nobody uses it. We have a slide here on Arduino App Lab. Is this just a reskinned Arduino IDE?
No, this is a significant departure. The App Lab is a unified environment designed specifically for this dual nature. The slide highlights dual language support.
Meaning you can see both brains at once.
You literally have Python code on one side of the screen and C++ on the other. You aren't alt-tabbing between a Linux terminal and the Arduino IDE. It's one project file.
That's slick.
And for the developers who hate graphical interfaces, the slide notes it is CLI complete.
Command line interface, so you can automate this.
You can do full deployment via command line. But for rapid prototyping, the most interesting part is the bricks concept. The visual shows a cube made of different colored blocks, like Lego.
Software Lego blocks, that sounds almost too easy.
It does, but think about the utility. Let's say you want to build a smart doorbell. You need to access the camera, run a face detection algorithm, maybe save a log to a database, and host a little web page to show the video.
Starting from scratch, that's what? A week of work. Setting up drivers, installing libraries.
At least. With bricks, these are prepackaged modules. You drag in a camera brick, an AI inference brick, and a web server brick. You snap them together logically. The slide claims you can build complex app skeletons in minutes, not weeks.
It sounds like it lowers the floor for entry. You don't need to be a Linux kernel expert to get a vision system running.
Exactly. It democratizes the thinking part, just like the original Arduino democratized the acting part.
I want to pivot to the physical reality of this thing, because prototyping on a desk is safe, but the slide from desk to field suggests this board is meant to leave the lab.
It outlines 2 modes. Mode 1 is your typical PC connection tethered to your laptop using your screen. That's for development.
Sure.
But Mode 2 is SBC mode, single board computer mode.
This is where it cuts the cord.
It runs as a standalone Linux computer. And this is where the hardware choices prove they aren't messing around. Look at the storage specs.
I see built-in eMMC storage, 16 GB or 32 GB, and it specifically compares it to SD cards. Why is that comparison so important?
If you have ever deployed a Raspberry Pi in a real-world setting, say inside a machine in a factory, you know the heartbreak of SD cards.
They corrupt.
Constantly. Vibration shakes the contacts loose. Or you pull the power plug without shutting down properly, and the file system corrupts. SD cards are consumer tech. They aren't meant for industrial OS drives.
And eMMC.
It's a chip soldered directly to the board. It's what's inside your phone. It's much faster, but more importantly, it is vibration-proof and far more resistant to corruption.
I see.
By putting eMMC on the board by default, they are signaling, put this in a robot that moves, put this in a machine that shakes, it will survive.
There's also a quirky little feature I noticed, the 8x13 LED matrix built right onto the board. It looks like a toy, almost, like something from a kid's coding kit. Why is that on a Pro board?
I thought the same thing at first, but think about headless deployment.
Headless meaning no monitor attached.
Right. You put this board inside a waterproof enclosure in a garden robot. You turn it on. How do you know if it booted? How do you know if it connected to Wi-Fi?
You usually don't. You just pray.
Or you hook up a clumsy external screen. With this built-in LED grid, you can program it to flash a check mark when Wi-Fi connects, or display an error code if the battery is low. It's a field UI. It's a brilliant, rugged way to get feedback without needing a fragile LCD screen.
That's such a smart, practical detail. Okay, we have to address the elephant in the room, or maybe the other small computer in the room.
Yeah.
We have a slide titled The Big Question, UNO Q versus Raspberry Pi 5.
It's the comparison everyone will make.
The Raspberry Pi 5 is a beast.
It is. The Pi 5 has Broadcom Cortex A76 cores. Those are significantly faster than the A53s on the UNO Q.
So for raw speed.
If your goal is to plug in a monitor, a mouse, and keyboard, and use it as a desktop PC to browse the web or edit spreadsheets, the Pi 5 wins. Hands down. It's a general-purpose mini PC, as the slide says. But the Pi 5 has no built-in microcontroller. It has no analog inputs. It relies on SD cards. If you want to control a robot with a Pi 5, you are back to the developer's dilemma. You have to buy an Arduino and plug it in via USB.
So the UNO Q isn't trying to beat the Pi at raw speed.
No. The UNO Q's philosophy is embedded intelligence. You choose the UNO Q if you are building a device, not a computer. If you need precise physical control based on AI decisions, like a sorter on an assembly line or a smart drone, the UNO Q gives you everything in one reliable package.
It's about integration over raw horsepower.
Exactly. It's about efficiency and architecture.
Speaking of horsepower, we need to manage expectations on the AI front. The slide on AI capabilities has a big reality check banner. I appreciate the honesty here.
It's very important. We are not running ChatGPT-4 on this board. You aren't going to be training massive large language models.
So what can it do? What is mobile class AI?
Think inference, not training. It's great at computer vision using models like MobileNet or YOLO. It can look at a video feed and say, person, car, defect.
Okay.
It's great for audio keyword spotting, voice commands, and it's perfect for integration, taking that data and making a decision. But it is an edge device. It makes decisions at the edge of the network. It doesn't replace a data center.
Yeah. So I shouldn't ask it to write me a poem, but I can ask it to recognize if my cat is stealing food.
Exactly.
Yeah.
You need to know, is that a cat? quickly and efficiently.
Yeah.
You don't need the philosophical implications of the cat's existence.
Fair point. We've covered the tech, the software, the competition, but I want to zoom out to the final slide in our stack. Strategic validation. This isn't just about a new product, it signals a business shift.
This slide discusses Qualcomm's acquisition of Arduino, and this is the context that makes the UNO Q make sense.
We usually think of Arduino as this scrappy open source company from Italy. Education, hobbyists, blinking LEDs, and Qualcomm is, well, Qualcomm.
They're a massive silicon giant. They are inside almost every Android phone on Earth. This acquisition is the strategic validation of everything we've just discussed.
How so?
It signals that the mobile tech giants realize that the prototyping world isn't just for hobbyists anymore. It's where the next generation of industrial devices is being born. The slide calls it a new era where mobile tech giants empower the prototyping world.
What does that mean for the guy in his garage?
It means supply chain access. Historically, you couldn't just buy a high-end Qualcomm processor if you were a small maker. You couldn't get the documentation, you couldn't get the support, you had to be Samsung or Google.
Right. You were locked out of the good stuff.
Now, through Arduino, we are getting access to enterprise-grade, silicon-like, that Dragon Wing processor in a form factor that is accessible to anyone. We are entering the age of seamlessly integrated AI thinking and real-time action. The barrier to entry for building smart devices has essentially collapsed.
And that leads us to the new category of tool summary. It says the UNO Q enables a single developer to build complex, collaborative, embedded systems speedily.
That's the key takeaway. A single developer. Before, to build a vision-guided robot, you realistically needed a team. You needed an embedded engineer for the motors, the C++ stuff, and the software engineer for the Linux and AI side, the Python stuff.
Because the skill sets were so different.
They were different worlds. Now, with the dual-brain architecture and tools like AppLab that bridge that gap, one person can span both worlds. It creates a full-stack hardware developer.
It effectively doubles the capability of the individual creator. You don't need a co-founder to build a prototype anymore.
It empowers the individual to execute on a complex idea from start to finish.
It's a pretty incredible journey through these slides. We've gone from the messy wires and the developer's dilemma, that frustration of trying to make things talk to a unified industrial-grade solution that fits in the palm of your hand.
It is the maturation of the maker movement. We're moving from, can I hack this together with tape, to how robust and professional can I make this?
And that brings us to the end of our deep dive on the Arduino UNO Q. We've seen how the dual-brain architecture solves the timing problems. We've looked at the RPC bridge that lets Python and C++ talk like old friends. And we've seen how this fits into the bigger picture of AI at the edge.
It's a compelling package. It invites you to stop fighting with your hardware and start focusing on your application.
Here is where I want to leave you, the listener, with a thought to mull over. We talked about how this removes the friction between high-level AI and low-level hardware. If that friction is truly gone, if the thinking and the acting are finally unified in a cheap, accessible package, what kind of devices will we see built in garages over the next year that were previously impossible?
That is the exciting question. When the tool gets out of the way, the creativity explodes. I think we're going to see home robotics take a massive leap forward.
I can't wait to see what people build. Thanks for listening to this deep dive.
A pleasure to explore this with you.
See you next time.